Hi everyone, this is group number 9. Our topic is image compression and analysis of hand-drawn artworks and campus photos using PCA SVD. Let me briefly introduce what we did first. We applied truncated singular value decomposition from a PCA perspective to perform low-rank image compression. We compared two types of images, hand-drawn artworks and campus photos, which have very different visual structures. To evaluate performance, we use MSE, PSNR, and CR. Overall, our results show a clear trade-off between reconstruction quality and storage efficiency, and the optimal rank depends on the image content. Imagine you're walking across campus and you take a high-resolution photo to send to a friend, or you want to back up a hand-drawn art assignment to the cloud. While phone storage seems large, the amount of image data generated globally every day is massive. Images are high-dimensional signals, and storing or transmitting them is actually very expensive. This is the motivation behind our topic, image compression and analysis using PCA and SVD. The problem is that most digital images contain a lot of redundant information. In simple terms, many pixels are very similar to the ones next to them, like pictures of the blue sky, so we don't need to store every single detail of every pixel. What we really need is to find the dominant modes, the first few singular values, or the most important features, and keep those while discarding the rest to save space without losing too much quality. Our goal was to apply truncated SVD to two different datasets, 30 hand-drawn artworks and 30 campus photos. We wanted to see how much we could compress these two different styles of images before the quality became unacceptable. To perform the calculations, we converted all 60 images into grayscale matrices. Our core method, SVD, breaks down an image, matrix A, into three parts, U, sigma, and V transpose. The most important part is the sigma matrix, which contains the singular values. These numbers represent the importance of different image features. When we look at these values, they usually drop off very quickly in a trend called decay. This decay is the key to compression. Usually, just the first few singular values carries most of the image's information. This explains why we can throw away 90% of the data and still see a clear, recognizable image. According to the Eckert-Jan theorem, truncated SVD gives us the best possible low-rank approximation of our original image at a specific size. In our experiment, we tested 5 different levels of quality, also known as ranks, where K, the rank, equal to 5, 10, 20, 50, and 100. We used 3 metrics to evaluate the results, MSE for error, PSNR for quality, and CR for the compression ratio. MSE, short for mean squared error, measures the average square difference between the pixel values of the original image and its reconstructed version, representing the cumulated error or distortion. PNSR, peak signal to noise ratio, is an expression of the ratio between the maximum possible power of a signal and the power of corrupting noise that affects the fidelity of its representation. Our data confirm that it's a trade-off. As K increases, the quality score goes up and the errors go down, but simultaneously, the compression becomes less effective. We found that image content has a big impact on the results. At the same K value, campus photos generally have higher quality scores than the hand-drawn artworks. This is because artworks often have sharp lines and high contrast edges. It's harder for SVD to accurately guess these components at lower ranks. We also observed a point of diminishing returns. After a certain point, increasing K only gives a tiny boost in clarity but uses up much more storage. In conclusion, truncated SVD is a powerful tool. It allows us to mathematically find a balance between file size and image quality. For future research, SVD could be compared with other methods like discrete cosine transform or machine learning compression. Thank you.